Hello, my name is Braden Stump, and I'm the Director of Product and Business Development at Aerosol Devices, which is now a division of Handic Scientific. And I am here today to do a YouTube training video on the BioSpot-VIVAS bioaerosol sampler. So how to operate it, how to sample with it, how to get good results, theory of operation. This should, as a kind of starting caveat, be decently comprehensive for all of the different renditions of the BioSpot-VIVAS. We are now currently at the BSS 315 model, which has adjustable flow from 8 liters per minute to 15 liters per minute, but should also work for the BSS 310, which is 8 liters per minute, as well as previous prototype versions, such as the BSS 300P and older versions. We're looking forward to making sure that you all can have high quality bioaerosol sampling. It's specifically my job and Aerosol Devices' goal to help all of you be successful in bioaerosol sampling. So feel free to reach out if this video is not comprehensive. I have a demo instrument over here, which although does not look, it's not fully boxed, doesn't have all the accessories. I should be able to do a physical demonstration as well of how sampling works and what you'll be doing to have a high quality bioaerosol and generally aerosol sample. So without further ado, let's begin. So just kind of starting off with the purpose of this presentation is we're going to be looking at high-level overview on the BioSpot-VIVAS first. So the theory of operation, so how the instrument operates. Also why this capture method is useful, just so that you can kind of be preparing your experimental setup in advance. Additionally, we're going to be looking at how to operate it. We're going to have the instrument out here. We're going to turn it on, show kind of the main things that you'll need to keep in mind in operation and setting up an experiment. And we're going to be working through a lot of the common hurdles, the questions, specific stuff like decontamination, other questions along the way. But great. Now on to theory of operation. I just want to start in advance by saying I'm not going to spend too much time on theory of operation, primarily because we have another YouTube video that describes this technique. And if you already have a BioSpot-VIVAS that you're being trained on, you see the allure here. So the theory is going to be more utilitarian for understanding how to get a high quality aerosol sample. But if you have more questions, reach out, or there are other YouTube videos on our page that can help describe how the process works. That said, while you're planning your experiments and trying to understand the value of this instrument compared to other bioaerosol and aerosol samplers, such as biosamplers, stuff like that, you're going to be thinking of kind of three primary niches that the instrument entails, and that is efficient capture of nanoparticles. So specifically, all of our instrumentation, all of our samplers, but the BioSpot-VIVAS as well, is able to capture particles, aerosol in the air from 5 nanometer all the way to 10 microns. That's a huge range, and that range also entails it has virus fragments, bacteria, fungi, microbes of many different types, as well as, of course, non-living material, but is able to capture particles across a very wide range with high efficiency, above 90% on the BioSpot-VIVAS. Additionally, one of the very cool new niches that we found of the instrument is viable capture of viruses, bacteria, other microbes, primarily because our capture technique is so gentle. We have seen in a lot of published cases, specifically with the BioSpot-VIVAS, very high capture, viable capture of viruses, bacteria, such as MS2 bacteriophage, SARS-CoV-2, and plenty of other bioaerosols along the way with the BioSpot-VIVAS. So that viable capture is cool. Also, generally, bioaerosol sampling, you're still able to very efficiently capture onto genomic preservative, into buffer, agar, so things like PCR, things like culturing, things like genomic analysis, sequencing, stuff like that is going to be possible along the way as well. And finally, the samples coming out of the instrument are concentrated and convenient and ready for analysis, ready to be pipetted out. They're sampling on the instrument into a little 35 millimeter Petri dish into your preferred liquid or substrate. So it should be pretty easy to work with these samples once you have captured them. That said, the main governing process here that allows the BioSpot-VIVAS to work is a concept in a kind of central engine called a condensation growth tube. So this moderated version of the condensation growth tube here, this is the technology that we license. We license it from a company named Aerosol Dynamics. So thank you to Suzanne Herring and Aranza and Greg and Steve and Nathan and all the other folks at Aerosol Dynamics. But I think I am going to move on to the next page to kind of describe this a little better. But the governing principle here is that there are three systems that actually mimic the human lung that allow this water condensation growth tube to operate. And once you've done this, you can pair it to collectors. Other Aerosol Dynamics utilizes it to pair it to counting with water condensation particle counters, but I'll be focusing on collection here. Three basic systems that allow a water condensation growth tube collector to operate with high efficiency. The first is airflow. So you are pulling aerosol in, has a bunch of particles in it, coming in at laminar flow into the growth tube. In the case of the BioSpot-VIVAS, interestingly enough, there are actually 8 parallel growth tubes, but just kind of we're looking at a picture of one of them right now. So airflow is flowing through here with aerosol in it at laminar flow, and then it is being shot out of a nozzle at the bottom of the growth tube. So airflow is one of the 3 main systems at play here. The second system at play here is water injection, having a wet wick. So there is a wick, kind of imagine a circle of like paper towel material, effectively, and much more expensive than paper towel, but going all the way down the length of the growth tube, allowing a hollow cavity with a wet wall on the outside of it. The BioSpot-VIVAS has water pumps that inject water onto this wick to keep this whole entire growth tube wet along the walls. And that allows, with water vapor on the walls, for the third governing system, these temperature changes to create supersaturation in the growth tube. So first system, airflow, second system, water, third system is temperature changes. So when you have this airflow through the growth tube, and when you have, so I'm going to check to make sure that we are still recording here. Great, perfect, we are still recording. When you have these temperature changes occurring in the growth tube, and you are going with this wet wick from a cold conditioner section, which pulls the airflow down to a certain temperature, into this warm initiator section, the delta T between this region, the quick jump in temperature, forces there to be supersaturation here in the initiator. So 120 to 140% relative humidity here. And what that causes to happen is water vapor from the wick forces itself and grows an aerosol particle into a much larger micron-sized droplet. And those droplets, as they grow, going along the growth tube down this way, are much easier to impact when shot out of a little inertial impaction nozzle here at the bottom. So we are growing these particles. One sec. I'm gonna hit annotate here. I believe that I should be able to annotate now. We are taking these particles and they are, there we go, inertially impacting onto the surface of the liquid there. Once you have done that, so you have your cold conditioner section, warm initiator region, the moderator region is effectively a development meant for ease of use. So this cool moderator actually pulls some water vapor back out of the flow stream while the droplets are growing so that your sample isn't too soupy, you don't have too much water gain, you aren't having to deal with as much condensation downstream. Additionally, there's a slight heating element on the nozzle to make sure condensation isn't forming there. And on the BioSpot-VIVAS, there's also a sample cooler / heater to allow you to control the temperature down here based on what your preferred microbe temperature is for viability or sampling or otherwise. Just before skipping on past the theory section, a few more interesting things about this technology. Because the flow is so gentle and there's laminar flow through here, even though the wall temperature it looks pretty warm. And on the BioSpot-VIVAS, it's actually 45 degrees Celsius. This is just an example slide. In the actual flow itself, you can see from this graph from Herring et al., in your flow stream, you're not even actually hitting that wall temperature across the majority of the pipe flow through the growth tube. So typically, you're not really needing to worry about thermal shock occurring here. And even if you are worried about the temperature in this region, the residence time, so the time that aerosol is traveling through the tube, is only like a fraction of a second, like 0.3 seconds, something like that. I can get you an exact number if you contact us. Additionally, one of the cool things, and also I should say this 3 micron here is not correct. The BioSpot-VIVAS does grow droplets much larger than 3 microns. Is that since there's this blanket of water around the particles when they impact as a droplet, the impaction onto this liquid surface is not only more efficient, it's also much more gentle, which is one of the reasons that we believe that viability is so much easier to maintain on our instrument compared to more conventional impaction methods that don't have this, droplet formed around them. So great. Next slide. So just wanted to give a few use case examples of the BioSpot-VIVAS that kind of allow us to specifically look at the BioSpot-VIVAS closer. So yes, the BioSpot-VIVAS is larger at 53 pounds, but it is, it's built to be rugged. It is built for its higher flow. This is the highest flow instrument for sampling that Aerosol Devices offers. Now, most instruments are currently at 8 liters per minute, but now with this adjustable range up to 15 liters per minute, it is a larger instrument than all of the other ones that we offer and meant to be rugged, transportable, field studies, chamber studies can handle it all. The sampling surface that you will be sampling onto, which we'll be looking at soon, is a 35 millimeter Petri dish. So just kind of a little, just a little sampling surface that you'll be able to add a liquid sample of any constituency if you're looking for collection media, or even solid surfaces or filter substrate. And we'll be talking about that soon. But generally, pretty large instrument. But what we have seen is a lot of success in ambient viable bioaerosol capture. There are plenty of other use cases that we have seen for the instrument, but one of the examples we wanted to highlight was from Lednicki et al. From University of Florida. So C.Y. Wu, John Lednicki, plenty of other people as well. It's worth looking at. They used 2 BioSpot-VIVASes and were able to capture viable SARS-CoV-2 during the kind of the height of the coronavirus pandemic. And they have since also published papers on capturing viable Delta variant and beyond, H1N1, MS2 bacteriophage. But generally speaking, you can see with the sampling that they did that they were able to use our instrument to capture viable bioaerosol, which we were very excited about, specifically virus, which is cool. But if you are looking for more information on other uses of the BioSpot-VIVAS, even just kind of inspiration for your own experimental setup, this paper and many other papers are featured in the reference section on our website and are a good starting point for understanding use cases of the instrument as stands. Go to the next slide. One other thing that I like to highlight here too is compared to other instruments, especially in the nanometer range, below 1 micron, you should be seeing this 90% efficient collection all the way across the size range from 5 nanometers to 10 microns. That is as long as your aerosol concentration is under 10 to the 5th particles numbers per cc, which we'll talk about later in our consideration section. But wanted to bring up, in this virus range, you should be seeing very high efficiency collection. So yeah, we're excited about that. One other example that we wanted to show off of this viable collection, this is from Mauha Pan at University of Florida as well, so the same group, is you should be seeing, compared to conventional sampling techniques, we typically, depending on experiment, a very high efficiency viable bioaerosol capture. But this great paper is on our website's reference section as well. Cool. So now that we have talked more about the theory and about use cases of the instrument, we're going to start talking about the practical things, unpacking the instrument, operation of the instrument, and actually operating it and getting your own samples. There are a few starting slides before we actually break open and start looking at our demo BioSpot-VIVAS here. But I'm really looking forward to showing you all kind of the nuts and bolts of how this thing operates. Cool. So first, just a caveat about experimental setup. Aerosol sampling, specifically bioaerosol sampling, is a very multidisciplinary field. You've got microbiology, biology, you've got aerosol science, aerosol physics, sampling. It is very hands-on, it is very hands-off. There's a very wide breadth of knowledge that you need to have in order to have a successful sample. And one of the things that we've noted is we want to make sure that out of the gate, we are providing as much information as possible to users to make sure their samples are successful. Feel free to always reach out to us. but we wanted to note a few things that are quick pitfalls for a lot of people not coming from the aerosol sampling world that they might miss that could reduce the quality of their experiments. Feel free to always contact us as well. I love talking about stuff like this. So first thing to note, when you are sampling aerosol, and let's say, if you're sampling ambient aerosol, that's fine. But if you are using tubing coming off of the inlet of your sampler, going to somewhere else where you're sampling from, let's say that it's an aerosol chamber. Let's just say you want a piece of tubing closer to your source, closer to the person sneezing that you're trying to pick up a sample from or what have you. You will need to make sure that all of the tubing and all of the fittings going from your aerosol inlet all the way to your source are made of metal or conductive material. The reason that this is because aerosol naturally in the atmosphere has some given amount of charge associated with it. It's a random sort of effect. There's, plenty of people use the charge of aerosol to their advantage. But what this means is that if you're not using conductive tubing, prior to entering the inlet of the instrument, walls of your tubing can build up a charge or a static charge of some kind and draw the charge of, naturally charged aerosol to the walls, causing them to be lost prior to being captured and entering our instrument. What that means is you'll have random losses in your aerosol sample that our instrument can't account for and that you all can't account for. So what we recommend, if you don't want to use metal tubing is, of course, perfectly fine. McMaster-Carr and other websites have static dissipative plastic tubing that you can put on the inlet. And then as long as you're using metal fittings to connect that to your aerosol chamber or, your size changes of tubing, then you're perfectly set. General recommendation, the inlet of the BioSpot-VIVAS is the smaller sized inlet. So the standard inlet on most of the previous samplers is 10 millimeter OD, which you can find 10 millimeter swage lock to attach to. I would recommend Teflon ferrules just so that you can remove it. If you need a part number, hit us up. If you're using McMaster-Carr, the static dissipative tubing, and you're having trouble finding metric options, the easiest thing to do is to buy 3/8 inch inner diameter tubing to go on the 10 millimeter OD inlet. That's because 10 millimeters is, of course, very close to what 3/8 is. 3/8 is 9.525 millimeters. So 3/8 inch tubing will fit perfectly on the inlet of the smaller inlets of the BioSpot-VIVAS. If you are operating one of the newer instruments, so the higher flow BioSpot-VIVAS now has a larger inlet, the inlet of that is 20 millimeter OD. And 20 millimeter OD accounts to, it's very close to 3/4 of an inch. 3/4 of an inch is 19.05 millimeters. So you should be able to buy from McMaster the 3/4 inch ID tubing, and it will fit very nicely on the larger inlets for the BioSpot-VIVAS, which are, as we talked about before, 20 millimeters outer diameter. That said, we'll go on to recommendation 2 for experimental setup. Thinking about where you'd like to place the inlet of the instrument is also a big thing. There's a paper that Brad Vass put out from University of Florida that showed where they were capturing a viable Delta variant from a person isolating with SARS-CoV-2. And one of the things that I really liked that they showed in their publication was where the instrument was in reference to the aerosol source, the sick person, as well as the HVAC inlets and returns around the building. So where they thought airflow was traveling in the room. That's a really big deal. If your aerosol sampler is on one end of the room and your patient or what you're sampling is on the other end of the room, and there's an HVAC vent pulling all of your air in between the two of those things, you would expect to not capture any of the aerosol that you're wanting to capture. So thinking about how can I get my sampling instrument as close to my source as possible? How can I make sure that I understand how the airflow in the room is moving? I mean, hospitals, for example, have a lot of air exchanges. So you really want to make sure that you think about where, and even if you're running tubing, like how far is my tubing going from my chamber to my instrument? Am I losing particles along the way based on their size? Is it drying out if I've got 10 feet of tubing going from the chamber to the instrument? So be thinking about how aerosol is getting to the sampler. Final recommendation, just make sure that tubing doesn't have kinks in it. Specifically, if you're looking at tubing that has a very fast 90-degree bend or something like that, then if you have a 10 micron particle flowing through that tubing, or even a 5 micron particle, stuff like that, if it can't round that corner fast enough, it's going to impact on the wall before entering the instrument. So just remember that effectively things coming into the instrument, you'll have to keep an eye on aerosol not being lost in advance. Great. The second thing that I was looking to talk with you all about prior to showing off the instrument, just because it's easier to see, and if you need a PDF version of the manual, this should also be in your manual as well, is the flow path of the instrument. I think it's easier to show here prior to us looking at the instrument. One sec. Great. So what you will see here with the flow path is that the three governing systems that we talked about, airflow, water, and temperature, are represented on this flow path. Your temperature system is represented by your conditioner, initiator, your moderator. There's also a slight heater for the nozzle just to keep condensation off of it, and then a cooler/heater for your Petri dish. So that's the temperature control setup. I'll get the eraser out. Next, you can see our water injection system. So coming from a supply bottle on the back of the instrument, and since we have 8 growth tubes, there are multiple valves and pumps that provide this, but there is water that injects into the initiator section of the growth tube to keep the wick wet. That's our water injection system. You can also wet the wick by using a syringe on the top of the wicks itself by removing the inlet, although that's a bit more manual. We'll talk about that once we have the instrument handy. And once water has entered the wick, if the growth tube is saturated with water and you start to see water dripping off of it, there is actually, prior to sampling into Petri dish, what we call a removal flow. So this airflow is much less than the main airflow of the instrument. It's about 0.35 liters per minute. And all that its job is that prior to aerosol and droplets impacting in the Petri dish, excess water is being removed off of the wick with a little bit of airflow. So water comes through this tube. It is deposited into this waste bottle, which you will be emptying and cleaning over time. And then that airflow is choked by an orifice and it goes out through an exhaust in the back. So this additional airflow, just as a note, this removal airflow pump has to be on. Water will not inject onto the wick unless your removal airflow pump is on. So you'll always want to make sure your removal pump is on. And of course, yeah, it does not let you inject water onto the wick unless your removal pump is on. So that is your kind of water removal system. And then from that point on, there is also airflow, the final thing. And also, big thing of note here, the way that we denote whether an aerosol sample is being taken or not is if the sample airflow pump is on, right? Are particles being taken from the atmosphere and deposited into the Petri dish? If yes, you have a sample running. So how long the sample airflow pump is on is what determines the length of your aerosol sample. So all of this is happening via a vacuum pump. Air is flowing through the growth tube, across the nozzles, being deposited into the Petri dish. So that's your sample flow path. And then air is flowing through the rest of this remaining path. 2 things of note here. You'll see that since the removal airflow and the sample airflow are both pulling from the same source, the inlet, that your inlet flow will be slightly different than your sample flow. The rotometer here on the back end should allow you to read what your sample flow is. But if you are looking to measure with some sort of external tool to get a really precise reading past what we set in the factory of what your sample airflow is, you'll need to connect to the instrument with a computer. And we'll talk about that in a bit. That said, the other thing of note here is that there are some protections against your Petri dish and sample overflowing. So if your Petri dish here overflows, that excess water is going to start traveling down this air line where air is continuing to go. And if that's the case, it will end up in this thing that we call the water trap bottle on the bottom of the instrument. If this trap bottle is filled with an appreciable amount of water, something is likely wrong on your instrument. This is a big troubleshooting zone. It is here to protect the downstream air componentry here. So airflow is traveling along this path. If you've got liquid in your trap bottle, it's probably from your Petri dish. So it's a big thing to keep an eye on. Then after that, that airflow goes through a filter and then goes through your rotometer flow here. So that will just be indicating to you what your airflow for your sample airflow is. And then through a needle valve, which this is going to allow us to control our airflow rate through our main pump and out the exhaust. You'll also note here, the exhaust of the instrument is filtered multiple times. And of course, we're already sampling the majority of bioaerosol here. But if you're wanting to attach your exhaust fittings and send them out to a bio hood or a hood of some kind, or HEPA filter them further, there are options to connect to that in that way. Got questions? Feel free to send me an email. Cool. Final thing we are going to look at prior to me turning my screen share off for a moment and us actually looking at the instrument is accessories. Because I have a demo instrument here, I don't have the box the instrument sits in, so I don't have all of the accessories looking pretty, so we'll be talking about them. I have some things like the power cable here, although it's not superbly interesting to show all of you guys. So we'll be talking about the accessories and then looking at the instrument in full over here. Sorry, getting some sort of water. There we go. So this is taken straight out of the instrument manual. So you should have these things based on what your manual says. One, the growth tube unit, that is actually just straight up the instrument itself. That is, of course, kind of the driving force in getting your sampling done. Additionally, the instrument will have an inlet cap on the inlet. It is just a red little cap that you can pull off. That's just to protect the instrument in shipping and make sure no gunk falls in it. You will also have a user manual. If you'd like a PDF version of the user manual, hit me up. I can send that to you. You will also have an AC power cord. This is looking, of course, a little small, but depending on your region, you will have a cord that you will be plugging into the back of the instrument and plugging into a wall outlet to turn the instrument on. Additionally, you will have a data stream cable. This data stream cable, what it is meant to do is allow you to communicate with the instrument and send it additional commands, and then also to read the log data that comes off of it. Since our instrument's an aerosol sampler and the settings are pretty locked in, you don't need the log data off of the instrument as it's sampling. But if that's something you're interested in for remote monitoring or to be able to send commands from a computer, there are benefits there as well. It's just a little printer cable it plugs in the back. You will also have some hex keys, some Allen wrenches, hex screwdrivers, however you call it, for removing the inlet, for removing the sample cooling module, stuff like that. I do not have that right now, so I'll be using my own set. And then there's also the water supply trap, waste bottles. We will be talking about those very soon. Syringes that are for wetting the wick or for kickstarting components. Pieces of tubing here that are also just for troubleshooting methods if you need them. But then also your Petri dishes, which we will also be showing off once I'm removing and replacing the sample on the instrument, which will be fun. The Petri dishes themselves are 35 millimeters in diameter and 11 millimeters tall. You can go, I believe, up to 15 millimeters in height, but there are constraints based off of the inside of the instrument that you'll want to keep an eye out. You can also buy your own Petri dishes if need be. Final two things. This coupling insert here, that is for taking the exhaust of your instrument and routing it to a hood or to a filter of some kind. So we'll show that off. And then finally, 10 millimeter inlet filter assembly. That is for running filter blank tests, running control tests, drawing your wick. Anytime you don't want aerosol entering the sampler, but you still want air entering the sampler, that is what your inlet filter assembly is for. Great. Cool. So I'm going to do my best to be, perfect with showing this off and talking about the instrument. I'll inevitably make some mistakes. I'm going to stop my screen share here, but feel free to contact us with questions, reference your user manual as well. But let's get kicking. So I have the instrument here in front of me. This is a BioSpot-VIVAS. It is, of course, pretty large. I'll be needing to move the camera around quite a bit. However, I will be talking about it as we go. The first thing that we're going to start with doing is, sorry, I have a paper in front of me, look at the externals of the instrument to understand what's going on. So let's pop on the inside here first. This is a demo instrument, so it's not as pretty. On the inside of the instrument, you will see we have the growth tube here: conditioner, initiator, moderator, nozzle. And then below the instrument, we will be looking at the sample Petri dish. On the top of the instrument, we have one of the more important things, the inlet. So the inlet of the instrument is, of course, where your aerosol is going to be coming in. It is where you are going to be attaching any tubing that you might be connecting, or I mean, it's where your sample will be coming in generally. If you have an older version, or if you have a current version of the BioSpot-VIVAS with a small inlet, your inlet will be 10 millimeters in diameter. If you have a higher flow version of the BioSpot-VIVAS and you're operating with the higher flow inlet, your diameter will be slightly larger. It will be 20 millimeters, like we discussed before. Something of note here, your instrument comes with a 3 millimeter Allen wrench, hex key, whatever you want to call it. You can remove the inlet of the instrument if you so choose for cleaning or for getting direct access to the wicks by removing these 4 screws here with the hex key. Please do not drop these screws into the growth tube. They are very hard to get out. I know that it is an inconvenient size, but make sure that if you're removing these, you are making sure that they don't fall anywhere. There's also a little O-ring holding the inlet in place. Oh, sorry, getting some glare here. There's also a little O-ring holding the inlet in place. You will want to make sure that that is seated well when you are reinstalling the inlet of the instrument, primarily because if there is a clip in the O-ring here, your inlet flow will not match the rest of the flow through your growth tube. So you won't be sampling all the particles that you possibly could. Just bad news. We want to catch all of them. So we'll go on to the front of the instrument here. There we go, putting these back. This here is, of course, the display. The display will be providing you information on the instrument as it operates. You also have a rotometer here. This rotometer, and there are different scales for different versions of the VIVAS, and also older prototypes do not have this on there. This is meant to indicate to you and tell you what the flow rate is of your sample flow specifically. So just what's flowing over the Petri dish. It will not be consistent, most likely, with your aerosol inlet flow, primarily because the water removal flow is also there. It's about 0.35 liters per minute. So your inlet flow will potentially be higher than what is reading out here, but it's meant to indicate that your sample flow pump is on, that a sample is running, and what your flow is onto the Petri dish, the actual aerosol you're sampling. Great. You also see on here a knob for opening the instrument's door. You will not need to do that very often. And since there are a lot of electronics in there, a lot of flow components, I would not recommend doing this unless Aerosol Devices asks you to do it, just to make sure you all, keep safe and that the instrument stays in good condition. And then finally on the front here, you will see 5 buttons. The black button here that says pump, this is for turning the air pumps, actually both of them, on and off on your instrument. Once I get the camera out and once we turn the instrument on, I will be showing that effectively it's how you press the button, whether you tap it or hold it, as to whether or not it turns on the removal pump, the sample pump, or both. Additionally, you will see here 4 buttons that allow you to control the menu structure on the instrument. So you see the enter button here. This is for going deeper into a menu or confirming an option. The up and down buttons here are for toggling through different menus. And then the escape option is for going backwards out of the menu. So it's pretty easy and pretty straightforward. This stuff can all be circumvented by utilizing serial communications with a computer on the instrument. So that's up to you whether or not you'd like to do that. You should be able to do everything with the serial cable plus a little bit more by connecting to the instrument with a computer versus the buttons. But a lot of people just like using the buttons. So we're going to rotate now to the back of the instrument and the sides of the instrument. We'll be looking at the bottom in just a moment. So there are, of course, convenient handles here. There are on the sides of the instrument fan guards for air to go in and for air to go out. These, and then of course handles to hold it. I do understand that the instrument is loud. The fans on the instrument are very loud. It is the result of needing to meet our specifications for the instrument being able to operate in high temperature and cool temperature environments from 10 to 35 C. If the fans are an issue and noise is a problem, you can contact us and we can talk through some potential solutions. But let us know as you go. Please do not block these fan vents though, because that is what is allowing heat to escape the box and keep the growth tube stages at temperature and keep things from malfunctioning. Additionally, if on the side of the instrument over here, where air comes in, if your instrument has filter material installed in here, if you're ever wanting to remove it, you can use a screwdriver to remove these 4 screws here, pull this little fan guard out, and you can either look at this filter material, shake it out, get the dust out, put water through it, let it dry, stuff like that. Or you can also fully remove it. The filter material in here is fully optional. We had a lot of people operating in really, 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 hair-filled, dirt-filled environments where they wanted blockage there. But if you remove the filter material, the instrument does get down to temperature faster. So as long as you're in an indoor air sampling environment, the filter material installed in here is optional, up to you all. Great. Let's look at the back of the instrument. So, as you can see, your serial number label is here on the back of the instrument. This is primarily useful if we at Aerosol Devices, you're in contact with us about operation of your instrument. It's nice to know our production files are pretty extensive, but they all tie to the serial number here. Additionally, you will see one of the many accessories that we noted in previous slides, the clean supply water bottle. This clean supply water bottle, you can see a little clip-in thing here where you press a button and this flicks into place, and then you can press it to open it again. This bottle is 500 milliliters, and you will be filling it with either distilled water or deionized water, anything distilled or cleaner, because if you use tap water to fill this bottle, it will slowly degrade the quality of your wick over time. So you're filling this with water, closing the lid again, sealing it tight, putting it back into place, and letting it click in. When operating the instrument and you're putting counts and injections of water into the instrument, you should be able to see liquid travel through this line. If you're wanting to decontaminate the instrument, which we will talk about later, you can also install isopropyl alcohol, methanol, ethanol, 70 to 100%, or even hydrogen peroxide of 3% into this bottle to inject into the growth tube. That's a way to clean your growth tube on the instrument. However, we do recommend, and I will talk about this later, flushing with double the amount of water afterwards, after you have installed cleaning fluid in here. We just want to make sure that we're not leaving something, that could be corroding or that could be volatilizing, could be affecting the quality of your next sample in the instrument. So we're flushing it out with water after it's been used to clean. The next thing you'll see here is also with a little push button here to remove the wastewater bottle. It's got these 2 lines because as we saw from the flow diagram, the water is flowing in and then air is flowing out to be filtered and sent out the exhaust. And this also, you can pop it open, pour out your gross stuff, clean it with some sort of cleaning fluid if you prefer. These bottles are HDPE, so they're very cleanable. That's high density, I think high density polyethylene is what it is, but it's very cleanable and can be removed, reinstalled, stuff like that. We'll start talking about the other parts of the back now. Firmware load, this little USB port, most people do not ever need. If you need to be uploading firmware on the instrument, you will be in contact with Aerosol Devices anyway, so I'll be emailing you no matter what. I'm going to leave it be for now just so it doesn't get messed with. Data stream here, this is where the cable plugs in on the instrument side that you then plug into your computer to talk to the instrument via serial commands and seeing data come out of it. So this is where you'll plug it in to be able to talk to it with the computer. Additionally, we have the little removal exhaust and sample exhaust here. These are the 2 exhaust ports coming out of the airflow lines on your instrument. One for the sample flow across the Petri dish, one for the removal flow being removed from the growth tube. These are both already filtered twice, but the instrument does come with fittings that you can push into here, and they click into place that have little barbs on them that allow you to take tubing to HEPA filters to hoods, stuff like that. And then finally, you will see a little flip switch here and a plug-in for your power cable. So this is actually how the instrument turns on. So what you will be doing, I'm not going to show this again once I turn the instrument around to turn it on, just because it's hard to show. But what you will do when you want to turn your instrument on is you'll take your power cable, plug, of course, one end into a wall socket, the other end with flat side up into this slot, and then you will flip the switch to turn it on, flip this switch to turn it off. That is how the instrument turns on. So when I turn the instrument on later, I'm doing that. Cool. Right. I'm next going to show off the bottom of the instrument, and then we can get to actually operating it. I turn my camera down just a little bit. Perfect. So what you are seeing here is the bottom of the BioSpot-VIVAS. This is where the magic happens for removing, installing your sample, stuff like that. So the first thing that we're going to point out is we're going to point out the needle valve. This here, by turning this, is what allows you to control the airflow rate on your instrument. There are some Vivases, like the new versions, that are 8 to 15 liters per minute, where this will be a greater adjustable range. And on some instruments, you're just making sure it's at 8 liters per minute. We do set the flow rate to 8 liters per minute sample flow at the factory before it leaves. But if you need to do any sort of adjustment, this is your spot to do it. Don't open it all the way. If you loosen it up all the way until it hits the end of the seal, it actually, just these swage lock valves, it doesn't seal anymore. So you might start to have a leak occur here. So always make sure that it's never opened fully all the way. Additionally, you will see over here, there we go, your trap bottle. This is the bottle that we talked about before that is right downstream of your Petri dish sampling, where if you see any water in here, something has probably gone wrong. So just keep an eye out for it and make sure that you're not seeing a ton of water in here. Finally, we are going to be looking at, this is the sample cooler and Petri dish holder. So the Petri dish sits actually within this area over here. And there is a little piece on here that installs via these 2 screws on both sides that sits on the bottom of the Petri dish holder to cool it to your preferred temperature. Something of note, you don't have to operate with this sample cooler or heater on. Some people don't like undoing the screws if they're running fast back-to-back 5-minute samples, and the quality of their bioaerosol, they're still going to get viable capture and stuff like that. So this is an optional component. The way that it attaches in, you'll see a little cable installed here that just sidles right on in, and you'll have to, it's a 1/4 turn connector right there. And then we're actually going to today operate without the sample cooler on. What that means, if the sample cooler is installed and plugged in, you will see it controlling to temperature on the front panel. If it doesn't, it'll show -32.2. That's just the default value from the temperature sensor. Nothing is wrong if you're seeing a negative value for temperature on the sample cooler when it is not plugged in. So we're going to unplug it. I'm going to show how this is unscrewed. This is the sample cooler, of course. There we go. Screw is undone on this side. As you can understand, it does take a little bit to get these screws all the way undone, which is why people sometimes operate with them off. This is up to personal preference. So now we have access to the Petri dish holder. All that you need to do to get access to the Petri dish holder here is unscrew from the bottom here. Perfect. If you ever need to clean the nozzle of the instrument, you can use hex keys here. You can actually remove this whole entire chamber. Or on newer versions of the instrument, you should just be able to have direct access to removing the nozzle to clean it with a screwdriver. So up to you. We don't typically recommend doing cleaning on this very often. You will not need to clean it very often, but if you do need to remove it, it's more of an involved process that you'll want to turn the instrument on its side to do. And by turning on its side, I mean turning kind of like this, if that makes sense. Actually, you can see it. Yeah, see the 4 screws holding the nozzle in right there. and the nozzle that actually samples on a Petri dish. So, great. We're going to look at the Petri dish now. This is the Petri dish holder on the instrument. So you can see here on this Petri dish holder, there's an O-ring at the bottom. There we go. That needs to be contacting and engaged in order for a high quality aerosol sample to occur, primarily because that guarantees airflow through the growth tube. So making sure to tighten this in pretty tight once it's installed is important. There have been a few different renditions of this Petri dish holder. So if you have an older version of the instrument, it might look different from this. It might not have as chunky of threads as this. Very scientific term, chunky threads, of course. But regardless, you can see here, the Petri dish sits into this little groove on the Petri dish holder. You can buy your own 35 millimeter Petri dishes as long as they're a height that fits into the instrument. And right now, I think is a good time, there we go, to talk about preparing your Petri dish sample. So this, of course, we've seen screws into the bottom of the instrument. We've also talked about that the BioSpot-VIVAS is an inertial sampler that samples from the jets, and they have particles, droplets, shoot down onto the liquid level surface or solid surface here. What that means is that the jet distance from the nozzle to that surface matters quite a bit. So what you will need to do is make sure that your distance from the nozzles to the surface you're sampling on is of a certain distance. What we mean by that is typically, if you have a 35 millimeter Petri dish, having somewhere between 1.5 milliliters and 4.5 milliliters in your standard Petri dish over time. That is at 8 liters per minute. If you're operating at a higher flow, the numbers change slightly. And plenty of folks have gotten very high quality aerosol sampling with just a filter in the bottom of their Petri dish or nothing in their Petri dish. So at your own risk, there are lots of modifications that you can make to your sampling method here. As far as what can go in this Petri dish, impaction is inertial, so we really don't care what the liquid or solid sampling surface is, as long as it doesn't eat through your Petri dish and can be easily sampled onto and not damaging any of your components here. So people have sampled into water, they've sampled into agar, they've sampled into phosphate buffered saline or other buffers with bovine albumin in them. They have sampled into artificial saliva. People have cut 30 millimeter filter substrate, membrane filter, aluminum foil and sampled onto them. The world is really your oyster here as far as your method of sampling, as long as you are just making sure that you've got stuff below the jet. That's really all you need for high quality sampling there. That said, once you get whatever you want to have in there, you will pop it in there. As long as your wick is wet, your temperatures are correct on their stages, what you'll be doing is you'll be turning on the sample air pump for as long as you want to sample. Let's say for a 5-minute sample, you turn the sample pump on for 5 minutes. You turn the pump off, you remove your Petri dish again, and your sample is complete. I'll check my notes here. I'm done Petri dish install removal. Sweet. As we turn the instrument on, I just want to say a quick reminder. Remember, 95% of the time, your sample will run properly if your wick is wet, your temperatures of your stages are correct, and your airflow pump is on and running through the entire growth tube. With that, I'm going to plug the power cable into the back of the instrument and turn this thing on. Okay, got my cable from before. I am going to have to be moving the camera around as we go. And the actual vision from the camera will be backwards. So apologize for the difficulty in reading, but we are going to be looking at the screen. So I should be able to describe a lot of stuff. Cool. Instrument is plugged in. I'm going to turn the camera this way. And I will be flipping the on switch on the back of the instrument to turn the instrument on. So as the instrument powers up, you will see the firmware version. You will see that it is a BioSpot-VIVAS, of course. It will tell you to check your water bottles as is customary. And then this screen will show up. So what this screen actually means, and I'm sorry that my hand is shaking, but it's going to probably be shaky like this the whole time, is these categories here, so from these two columns, are updating the current status of the instrument. And then the right-hand side over here is allowing your menu to tell you effectively changes that you're going to be making to the instrument. And I will go through all of these right now. C is the temperature of the conditioner stage, and you can see it's currently getting down to temp. I is the initiator temperature. So I'm sorry, I'm going to check my camera. There we go. I is the initiator temperature, so it's rising up to its warmer temperature here. M is the moderator temperature, so it is slowly going down in temperature to where we want it to be. N is the nozzle temperature, which I will talk about. It slightly heats. And then we see that sample here is reading as negative 32.1. That is because we have our sample temperature or our sample cooler removed right now. So that is correct. That shows as negative when it's not plugged in. A here is actually your ambient temperature or your case temp in the instrument. It typically is going to track pretty close to ambient in your room, although it won't be perfect. Finally, you can see this 0000. If you're operating with a sample timer, that is going to, of course, be showing what your current sample time is, although we don't have time to talk about sample timing on the instrument today. Honestly, a lot of people are, when they're running a sample on the Vivas, they're just using their phone to time it. But you're more than welcome to use the sample timer on the instrument. It automatically turns the pump off, and the actual instrument board has a real-time clock in it to time your samples as well. So whatever is easier. Additionally, you will see this in the top right-hand corner, something that says off. Where that says off, that is telling you the current state of the air pumps on your instrument. So now that I'm going to have this kind of pulled out a little bit further, we have our little pump button here that allows us to turn our air pumps on and off. So what I'm going to do first is I'm going to tap the pump button. You can't hear that right now, but there's a very slight change you can hear from the back of the instrument that the removal pump is on. And you can now see removal is showing here. What the removal pump is, as we discussed before, is removing water off of the bottom of the wick that is oversaturated. The removal pump itself has to be on to inject water onto the wick via the injection functions. And if you are wetting the instrument from the top of the you will really want it. We highly recommend, you need to have the removal pump on. So the removal pump is always on, even when you are running a sample, to make sure that your wick does not flood and your sample does not flood. If we tap and hold, if we tap and hold the pump button here, you will see, I didn't do it while the camera is in sight, so I'll do it again. You will see that our rotometer starts being in the correct position, showing that our sample pump is on. And when you see on here, it means that both the removal pump and the sample pump are on simultaneously. That is the base setting for when you are running a sample. So you'll see on when you are running a sample. If you are wanting to do some sort of very precise flow measurement where you measure flow at the inlet of the instrument here, that only has the sample pump on, you'll need to send the instrument a serial command to do that. Contact me or look in your manual. It's a bit too complex for today. But in the meantime, you can see sample pump is on. Rotometer is reading 15 liters per minute. That is standard for new versions of the instrument that have, of course, the higher flow capacity. On older versions of the instrument, you'll see 8 liters per minute on the rotometer. So what we'll do to turn the sample flow pump off is we will tap it again. So you can see it's all about tapping, turns off, turns on and off the removal pump, holding turns on the sample pump. So we'll tap it again to turn it off. And then if you tap it again, it'll turn the removal pump off. We're going to leave the removal pump on because we're going to talk about wetting the wick in just a moment. I think what we'll do is we'll talk about wetting the wick first, and then we'll talk about temperature stages next. So as far as menu structure on the instrument goes, we'll look at that too, but we want to look at our bottles first. So on the back of the instrument, we already looked at, there we go. Our supply and waste bottles back here. you'll want to make sure that your waste bottle is emptied and then your supply bottle is filled with water before trying to wet the wick. It's because the pumps that are running will be pulling water from the supply bottle and injecting it onto the wick, and then it's being removed to the waste bottle. If you are wanting to wet the wick in an alternative, faster method to kind of get it ready for a day of sampling, you can remove the inlet of the instrument and dose 6 milliliters of liquid directly onto the wicks here. This is also a valid way to clean the wicks, to take isopropanol and just use 6 milliliters on each of the 8 wicks. You'll need to flush with 12 milliliters or double the amount of water afterwards. But your removal pump needs to be on. Make sure the O-ring remains engaged, and this is tightened in nicely, and don't drop the screws into the growth tube. So it is a more manual method. I'll be going through our standard method of wetting the wick first. It does take longer, the standard method. So looking at menu structure, as I press up and down here, you will see a menu show up called temp. This allows us to change the temperature of each stage on the growth tube, which is cool. Additionally, you will see a menu called injection. This allows us to inject water onto the wick and in different methods. And then you'll see time, which talks about the sample timer. We won't be discussing that in this faster training, but it is in your user manual for setting a timed sample. That said, going back to, we're pressing up to go back to the injection menu. And if we hit enter on it, we can see an additional menu shows up here called PRD for period and CNT for count. The period function, if we hit enter on it, the little star by it means that it's our current selection, although we can go up and down to change those values. The period is for while the sample is running. Whenever the removal pump is on, the period function is operating. What this is this intermittently, it's at 120 right now, so it's injecting every 120 seconds, injecting 80 microliters of water onto the wick. So all that this means, and this is default for the current version of the BioSpot-VIVAS, older versions of the BioSpot-VIVAS have different defaults. So just operate with what your manual tells you to do. That said, this function just intermittently will inject water onto your wick over time. It is always on, so it's just meant for while you are sampling. I'm going to go back and down over to count. What the count function is, the count function wets the wick aggressively and quickly in order to get your wick wet prior to sampling. So if I hit enter here, and if I press up to 100 and hit enter, that will immediately start injecting 100 counts, quote unquote, of 80 microliters onto the wick. So when your wick is dry and it is straight out of the box and you're wanting to get water onto the wick to have it saturated and ready for a day of sampling, you will use the count function to do so. Something of note is that this count function here, you'll need potentially about 500 counts of water in order to wet the wick. But the way to tell whether the wick is wet is if your waste bottle on the back of the instrument, your waste bottle on the back of the instrument has water entering it, because that means that water is saturated enough on the wick that it is dripping off of it and that each stage has been wetted enough for high quality sampling. Great. That's how you wet the wick. Oh, also, if you're not seeing water enter the supply bottle, or if you're not seeing it being removed to the waste bottle, contact Aerosol Devices. You may have a problem. Temperature is the next thing that we will be looking at. So temperature, if we hit enter here, you will see conditioner, initiator, moderator, nozzle, sample, and it loops back. All that this means is this allows you to change the temperature of each of those stages. On the instrument itself, let's say, for example, conditioner we already know is 5. There's a star next to it, so we know the set temperature is 5. And the conditioner has actually reached 5, so it would be ready to sample there, actually. Actually, the whole instrument is ready to run a sample at 5, 45, 18, 28, and the sample is off. Let's say we want to change our moderator temperature. We would go, let's say we want to change it to 17. We would hit down to get the moderator temperature here, the set temperature to 17, and then we would hit enter to change that value. And because we see the star there, the moderator temperature is now set to 17. and the moderator is going to start getting down to that value. Now that our wick is wet, quote unquote, I haven't done anything to wet the wick yet, right? But let's say I wet the wick and our temperatures are correct. We can install a Petri dish and hold the pump button to start a sample. Once our sample's done, we turn off both pumps, remove our Petri dish. If your pumps are on and you try to remove the Petri dish, it's really hard to do. Pull your Petri dish out and your sample is complete. Fantastic. I have a few more things I want to talk about, but I think I can talk about it with the instrument off so that I'm not giving people vertigo or motion sickness from the camera moving around. So I'll set this over here. Fantastic. A few other things. We already talked about if you're wanting to verify airflow on the instrument, that you will need to send a serial command if you're wanting to verify just the sample flow with a rotometer, or sorry, with a dry cal or a gillibrator or air measurement tools like that. That said, we do have the rotometer on newer instruments to confirm airflow, and the flow rate of the instrument is set to 8 liters per minute sample flow prior to leaving our offices. Additionally, you can confirm inlet flow, removal and sample flow combined whenever you want with a flow meter of your choice. Additionally, let's talk draining and drying and storing the instrument. So because this instrument has warm sections inside of it, and of course a wet wick on the inside, that is a prime environment potentially for mold growth or for corrosion or other things we don't want to have happening to a high quality, beautiful instrument such as this. So what we recommend doing is you can leave the instrument wet as long as it has been decontaminated, we recommend, over the weekend. That's fine. Even a long weekend, not a huge deal. But if you want it to sit for longer than that, a week at a time, a few weeks, something like that, we recommend draining and drying the instrument out for storage. The reason we recommend this is so that you don't get mold growth, so your samples are high quality. And if it's shipped and returned, or if it's shipped somewhere else, it's in a high quality state and there isn't standing water in the instrument for some reason. The way that you do a drain and dry on the instrument, we learned how to use the count function in here. You'll empty both of your bottles, your supply and waste bottle, and then you will use counts, so you'll use the count function to clear the lines of all liquid. So you're trying to get all the water out of the supply injection lines. After that, you will then, of course, empty your waste bottle, and you're going to be setting the temperatures on your instrument here to warm. You're going to have the conditioner and moderator temperature at ambient room temp 20 C or above. That's just so that it isn't cold and you aren't condensing more water back onto your wicks, right? So then after that, what you'll be doing is you'll be running the air pump with the Petri dish holder installed. We are wanting airflow going across the wick, correct? For at least, we want 8 hours, at least 4 to 6 hours, but preferably 8 hours or longer. If you can leave it overnight, come back to it the next day in the lab, that's even better. All that you're trying to do here is with the temperature stages being warm, no water injecting onto the wick, we're wanting to blow air across the wick to dry it out over time. The other thing that you should be doing too, just because we don't want other particulate, other aerosol coming in, is have your filter assembly installed on the inlet of the instrument. This is, of course, because we don't want more particles coming in and making the instrument dirty after we've cleaned it. We'll be talking about decontamination in a little bit, but I wanted to make sure to bring that up. Draining and drying the instrument out. It's an important thing. And then the last thing that I had not yet talked about was temperature settings on the instrument. Typically, we recommend the conditioner and initiator stages being at 5 for the conditioner and 45 for the initiator on the instrument. That is because we want a 40 degrees C delta T, a change in temperature between the stages. If you're in a warm environment where you can't hit 5 and 45, as long as you're maintaining the same delta T, you should be receiving the same aerosol, droplet growth, high efficiency quality sampling. So it is fair game to have your conditioner at 10 degrees Celsius and your initiator at 50 degrees Celsius. That is acceptable as well. The moderator temperature is actually user controllable based off of how much, what you want your dew point of your downstream airflow to be, what you want your water vapor content in the downstream, aerosol flow to be. We typically recommend somewhere between 15 and 20 degrees Celsius. Although if you're wanting a very dry sample, you can go below 15, and some people need to operate above 20 degrees Celsius in order to get the samples that they want. But a great starting point is 18 degrees C on the moderator. For the nozzle, we're just trying to not have condensation occur on the nozzle. So it should be higher than the moderator temperature for sure as it's heated, and definitely probably higher than ambient temp as well. The typical recommended temperature for the nozzle is around 27 to 29 degrees Celsius. And then finally, for the sample, that is fully user controllable. Whatever you need your microbe to be at between 4C and above, that you would like it to maintain high quality viability or high quality, genomic quality as you're sampling, perfect. And you also don't need to have it on there if you'd like. So set the sample to whatever you need it to be for the quality of your experiment. With temperatures out of the way, just wanted to run across some error indicators for a moment. If the trap is wet, that's a problem. If the trap bottle here has water in it, that is rise for concern. Your Petri dish is blown out in some way. If you are not seeing water be injected from the supply bottle into the back of the instrument, or you're not seeing water removed to the waste bottle, that would be a problem. And then if you're getting unexpected results, poor results in some way, feel free to reach out to us and we can help you troubleshoot that. Great. With that, I think that we will hop back on over to screen sharing and get through the rest of our PowerPoint presentation. I'm going to move my camera back over this way. Hello, everyone, and share my screen. Cool. Back to the PowerPoint slide. We are now entering the special considerations part of this presentation. So special considerations, this is a little bit more specific, but I think that it helps a lot of people with sampling as well. Great. One big thing that we have seen come up a lot recently is related to aerosol concentration. Our sampler has very high efficiency sampling nanoparticles and above with high efficiency, high viability, all that stuff. However, it is using thermodynamics to do so. It is using water condensation on particles, which means that if there are too many particles in the air, specifically, we give a limit of about 10 to the 5th number per cc, or particles per cubic centimeter, then we are not going to be able to, in the instrument, condense on all of the particles to the right amount to grow them into droplets to capture them efficiency. So above 10 to the 5th number per cc, which you can hit on an aerosol chamber, you can hit it in environment, like if you're smoking a cigarette into the inlet of the instrument is the example I like to give, that you can hit that value unless you're using a dilution bridge or diluting your aerosol or making sure to keep track of your your chamber aerosol concentration. We can't promise 90% collection efficiency or high viability anymore. So I would keep an eye on that. If you have questions, please ask us. The big thing of note that's been of discussion with your customers and collaborators is that aerosol concentration number is any particle from 5 nanometers to 10 microns, right? We can capture across that range. So if you have a measurement tool for measuring your aerosol's chamber concentration that only measures down to 1 micron, you might be missing a lot of particles adding into that total concentration value between 5 nanometers and 1 micron. So something to keep an eye out if your results are not what you expect. Additionally, let's talk liquid level change when sampling. I'm going to go fast through this, but I want to make sure that people understand that this is something we're knowledgeable about and we can help your team with if you are sampling for long amounts of time. If you're doing a 5-minute bioaerosol sample, 10-minute, 15, even up to an hour, this probably will not be a big deal. However, if you're sampling in an ambient environment for a long amount of time, 2, 4, 6, 8, 12, 24 hours, you might start to see variation of the liquid level in your sample over time, causing issues for your experiments. We understand that this exists, and we want you to be thinking about what the concentration of aerosol that you have being sampled, the length of time you're sampling, and the volume of liquid that you'd like to maintain is, but we'll talk about why this happens and what you can do to control it. Once again, optional section here. If you're sampling for 5 minutes, 10 minutes, 15-minute samples, this is probably not for you, but for people getting longer ambient samples, this is for you. So I'm going to skip past the first part here, other than saying our ability to capture aerosol is related to having a liquid surface below our jet. Not a liquid surface hitting our jet, right? A liquid surface below our jet that we can impact onto. So actually a common misconception, the ambient relative humidity in the air actually does not have any effect on how much liquid you're going to be gaining in your Petri dish. That is because your initiator stage here is well over 100% RH. It's like 120 to 140% RH. So yes, high RH coming in means that you'll be condensing that vapor onto the conditioner stage. So it'll be harder for the conditioner to get to temp and you won't have to wet your wick as much. But it doesn't affect downstream liquid gain loss. What does affect downstream liquid gain loss is the temperature of your moderator and the temperature of your Petri dish. The moderator, since it's downstream of the initiator section at 120, 140% RH, it's at 100% RH, fully saturated air. And the temperature you choose for the moderator affects how much water vapor is in 100% RH air, right? Because cold air can't hold the same amount of water as hot air. So if we take a look at an example here, if you've got your moderator relatively warm, 20 degrees Celsius, and your Petri dish is at like 10 C, you're going to be gaining a lot of liquid volume as your sample time goes on, just from water vapor condensing into your Petri dish. So that is, an example of got a lot of water, gaining from warm moderator holding more water vapor, cold Petri dish causing condensation to occur. Inversely, if you have a cold moderator, 10 degrees Celsius here, and then if you have a decently warm sample, you're not controlling temperature, let's say 20 degrees C, about room temp, you will be probably evaporating volume as time goes on. This is independent of your aerosol droplets coming into the Petri dish. So we're going to be talking about that in a second. But long story short, cold moderator or relatively cold moderator compared to Petri dish, you're going to be getting evaporation of your sample over time. And this may not be a problem. It's technically concentrating your sample. The evaporation, you're probably not losing your sampled aerosol, but it is different from what you entered. So depending on your downstream process, this may be an issue. If you're sampling onto a solid substrate like membrane filter, this probably isn't a huge deal to have it dry out. Cool. The final thing to consider here is your concentration of aerosol. So every time that you are, an aerosol particle enters your sampler, you're growing it to a micron-sized droplet, right? Like 4 micron, 5 micron, whatever per the sampling instrument it is. And then that droplet with water, with a volume, is adding to the volume of liquid in your Petri dish. So if you sample a higher concentration of liquid, right? If you have if you're sampling smoke or if you're sampling from a chamber, you'll be adding a lot more liquid than if you had no particles entering at all. So if we look at a sample where you have a filter on the inlet, that's a more controlled case because you're just looking at water vapor, kind of a thermodynamic equilibrium, right? And that's a good way to check and kind of start out and get a good set point. But the concentration does have a notable effect on what your liquid gain loss is. That said, the stakes here are if you evaporate all your liquid sample out, your sample's gone. And if your sample fills with liquid to a point where your liquid level hits the tip of your nozzle, it blows your whole entire sample out into the trap bottle. Sample's contaminated, got to clean your nozzle, not very fun. So yeah, we recommend dialing in your moderator temperature and sample temperature to where you don't see much gain or liquid in your Petri dish. That said, concentration is going to change. Aerosol is not perfect. So it's hard to dial in perfectly, but a good place to start is 18 degrees Celsius on the moderator, 12 degrees Celsius, or whatever you want it to be for your microbe on the sample, and then dialing your moderator temperature up and down until you're not seeing too much gain and loss in your samples. Moderator down if you have too much water, moderator up if you need more water or liquid. Great. Final thing that we are going to talk about, we are very close to done, is growth tube decontamination. With our instrument being a bioaerosol sampling instrument, we know that it's a big deal to do two things. We don't have cross-contamination because we want high-quality bioaerosol samples that are not, influenced by the previous sample. and we want to have our human operators of the instrument, human subjects, anybody in range of the instrument being protected from, whatever is in there. So that's the reasons we want to decontaminate the instrument, as I'm sure you all already know. So something to think about, the way that we're going to be recommending how often to clean the instrument is related to your concentration of aerosol being sampled, how dirty your environment is. Are you doing chamber studies? Are you doing ambient studies? Stuff like that. Your type of bioaerosol being sampled, definitely different sampling pollen versus Ebola, right? And then your preferred decontaminating material. So isopropyl, hydrogen peroxide, water, whatever you're looking to do. So as far as your chemical used here, we typically really like isopropyl alcohol, but we understand that for some genomic studies, you can't use IPA. But isopropyl alcohol, methanol, ethanol, 70 to 100%, totally fine. Vaporized hydrogen peroxide, the whole instrument is clear to be used with vaporized hydrogen peroxide. For cleaning your nozzle, your vials, you can remove them, autoclave them, sonicate them, stuff like that. And if you want to use liquid hydrogen peroxide, you'll just need to flush with water afterwards. The maximum allowable amount is about 5% H2O2. But if you want to use other chemicals, contact aerosol devices. The key here is that we don't want to leave it sitting for too long, so we want to flush it with water after we've cleaned it. But we do have chemicals used in the materials used in the instrument here. They are all pretty chemical resistant. And we've had a lot of people decontaminate the instruments, but we like to bring that up. Cool. So first thing we're going to talk about is cross-contamination. I'm going to grab a little annotation tool right here. And wanting to make sure, okay, perfect. Cross-contamination is only going to occur here from the inlet of your instrument down to your Petri dish. That is because, there we go. Aerosol. One sec, I'm going to make sure that I'm sharing the correct screen before I start talking longer. Perfect. Okay, great. Aerosol is coming through the inlet of the instrument, and then it is there. Getting down to the Petri dish, and then after that, all of these other downstream components here aren't making contact with your sample anyway. You've got water injecting here, right? But this isn't touching your Petri dish. So that's really the range we care about, which, that growth tube region is what's getting wet. It's what the bioaerosol is traveling through. That's your cross-contamination potential zone. I'm going to get my mouse out. One of the things that we like to note is since the flow path of the instrument is straight, the airflow is gentle, we have laminar flow through here, aerosol doesn't typically quote unquote jump off of the wick back into the flow stream unless it's like amines or something really sticky or something that like really, high concentration aerosol samples. Most bioaerosol sampling users that we see, they are not decontaminating between every run because you're not getting cross-contamination between every run, especially at low concentrations and even during most chamber studies. The way that we recommend confirming this is at the end of the amount of time you would like to sample before doing a decontamination run. So at the end of a day, at the end of a week, at the end of a month of sampling, run a blank sample. So put a filter on the inlet, that there's no aerosol coming in, and run a sample of the same length that you normally would. Do whatever you normally do to it, PCR, culturing, sequencing, whatever downstream. And as long as it shows up 0, as long as it shows up a goose egg, as long as it does not show positive for what you're trying to sample, you know that your control works and your length of time going between a decontamination is correct. We typically recommend for users of the instrument, you're doing chamber studies, so high quantity of aerosol, high concentration of aerosol, to either decontaminate at the end of a day, decontaminate the growth tube, or at the end of a week at the most. Some people do a week, some people do a day. If you're doing ambient sampling studies, you should either be decontaminating at the end of a week, preferably, so you're leaving it sitting over the weekend in a clean state. Some people decontaminate at the end of a month. That's probably as far as you could run it. Depends on your concentration of aerosol. If it's not biological, you probably can wait until the end of the month, right? That said, that's our kind of recommendation for cleaning from a cross-contamination perspective. And also, stuff isn't jumping out at you and it's not growing. Once the instrument's sitting, your personnel is safe as well. I'm going to have this is the nozzle on the instrument is not stainless steel. There's not a valve. This is a wrong note here, so I'm just going to cross that out. The remainder of the flow path here, you've got your water bottle here coming through that you can install. You can put cleaning fluid into, like we talked about. You also have your inlet of the instrument, which you can remove and dose your cleaning fluid directly onto the wick, which actually takes less time and it's pretty easy to do. But the rest of your flow path either cleans itself or does not need too much cleaning. So excess cleaning material removed from the wick goes directly to the waste bottle, and you can remove the waste bottle, which is HDPE, and clean it. And then, your sample flow path here goes straight to the trap bottle, which you can remove and clean. Past that, so looking at your coalescing filters, your orifices, your otometer, your needle valve, flow pumps, you shouldn't have liquid in this section of the flow path. Your coalescing filters here, the 4 of them, are catching that, catching anything that isn't captured, because most everything is captured, right? So it's not going to be externally dangerous, stuff like that. And we really do not want liquid in these orifices, rotometers, needle valves changing your flow measurements. So we wouldn't recommend doing any sort of deep cleaning in these regions. Cool. Cross that out. Great. Next slide. Finally, cleaning the outside of the case. VHP is fine, alcohol wipes fine. This is all stainless steel or black anodized aluminum or powder coated aluminum. So most every preferred cleaning material, like a Clorox wipe, is totally chill. If you have questions, though, please feel free to reach out to us. Finally, this is the end of the presentation. Thank you very much for being here for this BioSpot-VIVAS training video. I still want to be in contact with you all, so please, if you have experimental setup questions, if I made a mistake somewhere, if you want a copy of the user manual, please reach out. It is my job and also my pleasure to make sure that you all have high quality, good bioaerosol sampling, improving the future of science in the world. So please reach out if you have any questions. But hope this was as comprehensive as possible to get you all set up. With that, I'm going to end the call as well as end our time doing this Zoom today. But please feel free to reach out if you have any questions, and best of luck in sampling. Bye.